Hello everyone, welcome to this lecture. The plan for this lecture is as follows. In this lecture we will recap some of the basic facts about algebraic structures. Specifically we will consider groups, we will discuss the definition of groups, the properties, and we will see some examples of groups. Looking ahead, these concepts will be used when we will design protocols for secure multi-party computation. So, let us begin with the definition of a group. So, consider a set capital G with some binary operation small o, and when I say binary operation, by that I mean it operates over two operands, okay. And both the operands will be from your set G. So, the set G along with this operation O will be called a group if certain conditions are satisfied. So, let us see what are those conditions. Those conditions are often called as group axioms. So, let us see those group axioms. So, the first group axiom is the closure property, which I denote by G1. So, G1 you can imagine as property number 1. So, the closure property demands that you take any pair of elements A and B from the set G. Okay. I stress any pair of elements. So, that means your A could be same as B as well, or your A could be different from B. So, the closure property demands that if you take any pair of elements from the set G and you perform the operation small o, treating the elements A and B as the operands, then the result will be should be an element of the G itself. That is why it is called closure property. Closure in the sense, imagine G is a big circle which has several elements, and you take any two elements from this circle A and B and you perform the operation O between A and B, you will obtain some element C. That element C should also lie within the circle itself. It should not go outside the set capital G. That is why the term closure property, okay. And this should hold for every pair of elements A and B from the set capital G. That is the closure property. The second property is the associativity property, which says the following. You take any triplet of elements A, B, C, again any possible triplet. That means it could be the case that A, B and C are all different. It could be the case that all of them are same. It could be the case that A and B are same, C is different, and so on. So, the associativity property demands that it does not matter which triplet of elements you choose from the set capital G. If you perform the operation O first over A and B and then you take the result and apply the operation O with C, then you get the same element which you obtain by first performing the operation O involving B and C, and then whatever result you obtain, you take that element and apply the operation O with that element and element A as the operands. That means it does not matter in what order you perform the operation O involving these triplets of elements, the result will be the same group element. Okay. So, if this property holds, then we say that associativity axiom is satisfied. So, that is the second requirement from a group. The third axiom that should be satisfied is the presence of a special element which we call as the identity element. So, there should exist some special element, let us give it a name small e, and that element should be a member of the set G itself, and that element will be called as the identity element. Okay. So, what do I mean by the identity element? By identity element I mean that you take any element A from the set G and you perform the operation O between the element A and the identity element E, you should get back the element A. So, that means if your G is say A1 up to AN and there is some special element E there, what we demand that the E should have the property that if you perform the operation involving A1 and E, you should get back A1. If you perform the operation between A2 and E, you should get back A2. If you perform the operation between AN and E, you should get back the element AN, and in fact, if you perform the operation involving E and E, you should get back E, because this requirement is for every A from the set G. So, even E will also be considered as an element A, right. So, if such a special element E is present, then we say that it is the identity element, and the third group axiom demands that your set G should have the identity element with respect to your operation O. Okay. So, this element E will be considered as the identity element with respect to operation O, right. And the fourth group axiom demands the presence of an inverse element for every element small a in your set G. So, what does it mean? The demand here is that you take any element A from the set G corresponding to this element A, there should exist some element from the set G. Let us use the notation A power minus 1 for that element, and the property of that element A power minus 1 should be the following. If you perform the group operation involving the element A and the element A inverse, you should get back the identity element. Okay. If that is the case, then we say that A power minus 1 is the inverse element for the element A with respect to the operation O. So, if your set G is such that operation O satisfies the closure property, associativity property, the existence of identity is guaranteed and the existence of inverse is guaranteed, then the set G along with the operation O will be considered as a group. Whereas, even if one of these 4 properties is violated, then G comma O will not be considered as a group. Okay. So, before I proceed further, few remarks here. The operation O need not be commutative. That means, it is not necessary that the result of A operation B and the result of B operation A is the same group element. Of course, there will be some group element because of the closure property, but that does not mean that the result of A operation B is the same as the result of B operation A, even though the associativity property is true. Okay. That is the first thing to note here. And the second important thing to note here is that this notation A power minus 1 is just a notation for a special element denoting the inverse of the element A. You should not consider it as A power minus 1 in the numerical sense, namely you should not consider A power minus 1 to be same as, is not, basically what I am saying here is that A power minus 1 is not same as 1 over A, because at the first place the element A need not be an integer value, it is just an abstract element from an abstract set G. So, it is just a representation, that is all. Okay. So, now let us see some examples of groups. We will start with the groups which all of us are familiar with, and then we will introduce some of the interesting class of groups which we will encounter in this course. Okay. So, all of us are familiar with the set of integers which I denote by this notation Z, and you consider the operation plus. So, that means I am considering my set G the abstract set G in the previous slide to be the set of integers, and I am considering the operation O to be the plus operation. Now, let us see whether all the group axioms are satisfied with respect to this set of integers and the plus operation. So, the closure property is guaranteed because you take any two integers a comma b, then their summation will also be an integer and will be a member of the set C. The plus operation, namely the integer addition operation, is associative. That means it does not matter in what order you add A, B, C, you will obtain the same result, same answer. The integer 0 will be the identity element, because you add 0 to any element A, any integer A, you will get back the integer A, and the integer minus A will be the inverse element for the integer A, right, because if you add minus A to the integer A, you will get back the identity element which is 0, right. So, here basically 1 upon A, or actually A power minus 1 is nothing but the negative A as per our notation for inverse of A. Okay. So, now if you are wondering that why I am considering the set of integers, why can't I take the set of non-negative integers, and by non-negative integers I mean all the positive integers and 0 is not included. Okay. So, that set is denoted by this notation. Now, let us consider this set Z plus and the operation to be the integer addition, and let us see whether all the 4 group axioms are satisfied or not. So, of course, closure property will be satisfied because you take any two positive integers, add them, you will again obtain a positive integer. Addition of integers is anyhow associative. Sorry, so I defined the set of non-negative integers incorrectly. When I say the set of non-negative integers, it includes 0 as well. So, my set Z plus is basically all positive integers including 0. So, negative integers are excluded. So, my axiom G3 is also satisfied because the integer 0 will be the identity element, but the fourth requirement, namely the fourth group axiom, is not satisfied, because if you take any positive integer, say if A is equal to 2, then the inverse of A will be the integer minus 2, but minus 2 does not belong to the set Z plus, because the set Z plus is not allowed to include the negative integers. So, even though the inverse is there, but the inverse is not present in the set Z plus, whereas the requirement of the inverse is that it should be a member of the set itself. So, that is why the axiom number G4, the fourth group axiom, is not satisfied, and that is why the set of non-negative integers with respect to the integer addition does not constitute a group. Okay. So, now let us see another very simple example of a group. So, consider the set of non-zero real numbers. So, the set of real numbers is denoted by this notation capital R, but I am excluding 0 from it, and my operation is now the multiplication operation, usual multiplication operation. And now let us see whether all the group properties are satisfied. So, the closure is satisfied because you take any two non-zero real numbers, you multiply them, the result again will be a non-zero real number. The multiplication operation is anyhow associative. So, it does not matter in what order you multiply 3 non-zero real numbers A, B, C, you will get the same result. The real number 1 which is a non-zero real number, will be the identity element for every non-zero real number, because you take any non-zero real number A and multiply it with the element 1, you will get back the element A. And what will be the inverse element? So, if you consider a real number A, its inverse will be 1 over A, because when you multiply 1 over A with A, you will get back the identity element, which is 1, and the element 1 over A is well defined. Why it is well defined? Because since A is a member or A is a non-zero real number, A cannot take the value 0, and that is why 1 over A is well defined, and 1 over A is also going to be a non-zero real number, and it will be a member of your set R minus 0. So, here in this case the abstract set G is the set of real numbers excluding 0, and your abstract operation small o is basically the multiplication operation. And we have shown that all the 4 properties are satisfied, that is why it constitutes a group. So, now you might be wondering what happens if I include 0 as well in this. That means, if I consider the full set of real numbers and my operation is multiplication, will it constitute a group? Well, the answer is no, because the inverse element is not defined for the element 0, because the inverse will be 1 over 0 and 1 over 0 is not well defined. It is not a member of the set of real numbers, right. So, that is why we are excluding 0 here, and then only we can prove the group axioms. So, now let us consider why we have taken now let us discuss why we have considered the set of real numbers, why not the set of non-zero integers. Can we say that the set of non-zero integers constitute a group with respect to the multiplication operation? So, let us see which properties are satisfied. So, the closure will be satisfied because you take any 2 non-zero integers, multiply them, the result will be again a non-zero integer. Multiplication operation is anyhow associative. The integer 1 will be a member of this set and will be the identity element, but the problem is that the inverse for integer A is not well defined. Say for example, if A is equal to 2, then the inverse of A will be 1 over 2, but 1 over 2 is not a member of the set of non-zero integers. Okay, it belongs to the set of real numbers. So, that is why axiom 4 is not satisfied, and hence the group hence the set of non-zero integers that not satisfy the group axioms. Okay. So, we have seen till now examples of groups which we are familiar with, namely the set of integers, real numbers and so on. Now, we will introduce 2 interesting groups which we will encounter later when we design MPC protocols. So, the first group I define here is the set Zn, and what is the set Zn? It is the collection of integers 0 to n minus 1, and basically you can interpret this set Zn as the set of integers modulo. What does that mean? You take any integer. Okay, so, you have the set of integers. Okay, we have the number line 0, 1, 2, and then in the positive direction you go towards infinity, and in the negative direction you go towards minus infinity. This is your set of integers z. You take any integer and divide it by the number n, you will obtain a remainder, and the remainder will be in the range 0 to n minus 1. Okay, you divide any integer, the remainder will be in the range 0 to n minus 1. So, that is why you can imagine that set Zn is basically the entire infinite set of integers reduced modulo n. Okay, so, basically I am collapsing an infinite set to a finite set by taking modulus or mod with respect to the modulus n. So, that is the interpretation of your set Z n here, and I am going to define a special plus operation here. Okay. So, this is called addition, but modulo n, and the notation that we use for this special plus operation is this. So, you have the usual plus operation and then you in the subscript you have the modulus capital N, and how this addition operation is performed. So, if you have two numbers a and b in this set 0 to n minus 1, and if you want to obtain the result of addition modulo n, what you do is you first add the two numbers a and b as per the usual addition operation, and then you take the modulo n. That will be the overall result of a plus b modulo n. That is my definition of addition modulo n. Now, my claim is that if I consider my abstract G to be Z n, and if I consider the abstract operation to be this operation of addition modulo n, then all the group axioms are satisfied. Let us see. So, you take any pair of elements a b from the set Z n, namely a is some element in the range 0 to n minus 1, b is also an element in the range 0 to n minus 1, and then if you perform the addition of these two elements a and b modulo n, whatever is the result of a plus b, as soon as you perform modulo n, the remainder will be in the range 0 to n minus 1, let that remainder be r, and the remainder will be in the range 0 to n minus 1, and hence it will be an element of the set Z n. So, that is why the closure property is satisfied. Okay. Now, let us see whether the associative property is satisfied or not, and it turns out that it does not matter what are your elements a, b, c. If you pick them from the set Z n, then it does not matter in what order you perform the operation of addition modulo n. The final result will be the same as a plus b plus c modulo n. Okay. You can verify that very easily. The integer 0, which is a member of the set Z n, remember Z n also has the element 0, will be the identity element, because if you take any element a in the range 0 to n minus 1, and if you do a plus 0, basically you are still having the element a only. And now, if you take a modulo n, the result will be same as a. Okay. So, that is why the element 0 constitutes the identity element here. Now, what about the inverse? So, the inverse of an element a. So, imagine that your element a is some element in the range 0 to n minus 1. Now, I consider an element minus a, and this is not the usual minus a. Minus a here is defined to be the element n minus a. That is the interpretation of this notation. When I say equal to and top of that define I write, that means I am giving a definition. That means I am now defining a new way or new interpretation for minus of a. Minus of a, my minus of a is now interpreted as if the difference of the modulus and the element a, and if your element a belongs to 0 to n minus 1, right, then it is easy to see that n minus a will also be an element of 0 to n minus 1. Okay. And what can you say about the result of addition modulo n involving a and n minus a? Well, it will be same as a plus n minus a, you add them and then you take a mod as per our definition of addition modulo n, but a plus n minus a at the first place will give you n, and now n modulo n will give you the element 0, which is your identity element. Okay. So, that is why the inverse element also exists and the inverse element will be n minus a. So, now you can see that this is a special type of addition operation defined over a special set Z n and it satisfies all your group axioms. Now, let us define a special form of multiplication over a special set and we will prove that that constitutes a group as well, and this is a very interesting group which we will encounter later. So, earlier we had defined a set Z sub n which consists of all the remainders that you can obtain by dividing any integer by the modulus n, namely it has the elements 0 to n minus 1. Now, Z n star is the collection of all the elements from Z n which are co-prime to n. So, GCD of a comma n equal to 1 means that a is co-prime to n and GCD means the greatest common divisor. So, co-prime means there is no common integer other than 1 which divides a and n, okay. That is the greatest common divisor here. So, for instance, 3 and 6 are not co-prime, okay, because their GCD is 3, okay. 3 divides 3 as well as 6. So, and that is not equal to 1. So, their GCD is more than 1, it is not 1, that is why they are not co-prime. But if I consider say 4 comma 7 are co-prime because their GCD, namely the greatest common divisor, is 1. Okay. So, what is my definition of Z n star? So, Z n had the elements 0 to n minus 1. Among all these elements, I am focusing on only those elements which are co-prime to my modulus. That means, I am considering now. So, if this is your Z n, I am focusing on a subset of Z n which I am calling as Z n star, which basically consists of only those elements from Z n which are co-prime to my modulus n. Okay. And now, analogous to the addition modulo n, I define the operation of multiplication modulo n and how it is defined. So, the first of all the notation is this. So, we use dot typically for multiplication, but now we are going to do multiplication with respect to a modulus, namely capital N. So, in the subscript we have that modulus, and if you have two elements A and B in the set Z n star, then the result of multiplication modulo n of A and B will be computed as follows. You first multiply A and B as it is as per the integer multiplication, and then you take a mod with respect to the modulus n. That will be the result of A multiplied with B modulo n. Okay. So, now we can prove the following. If I consider my set G, the abstract set G to be Z n star, and my abstract operation O to be the operation of multiplication modulo n, then all the group axioms are satisfied. So, let us prove that. So, let us prove first the closure property. So, imagine you take a pair of arbitrary elements A B from Z n star. I have to show that if I perform if I multiply A and B modulo n, then again I obtain an element from Z n star itself. Okay. So, since A is an element of Z n star, that means A is co-prime to n, that means their GCD is 1, and similarly B is an element of Z n star, that means B is co-prime to n, their GCD is 1. Now, I have to show the following. I have to show two things. I have to show that when I perform when I multiply A and B modulo n, then I obtain something which should be of course in the range 0 to n minus 1, plus it should be co-prime to your modulus n. So, two things I have to prove. So, the first thing is easy to prove. If I multiply A and B and then take modulo n, of course, the remainder R will be a value in the range 0 to n minus 1. But I also need to prove that this remainder R, which is the result of A multiplication B modulo n, is co-prime to your modulus n. Then only I can show that R is actually a member of Z n star, because that is my definition of Z n star. How do I prove that R is co-prime to n? Well, that is very simple. Okay. So, I can write R to be the difference of A times B and some multiple of your modulus n. Why so? What is R? R is the result, or R is the remainder which you obtain by dividing A times B by the modulus n. That means, it is the leftover portion. That means, I can say that A times B is equal to some k times n plus R by your division property. Okay. If A times B is completely divisible by n, then R is the remainder R will be 0, but if A times B is not completely divisible by n, then there will be a leftover remainder, that is your remainder R, and k is basically your quotient. Okay. So, that is why k is some integer, it could be 0, it could be 1, it could be some integer. And since GCD of A and n is 1, that means there is no common divisor of A and n apart from 1, and since GCD of B and n is also 1, because both A and B are co-prime to n, then I can conclude that A times B is also co-prime to n. Why? Because if GCD of A times B of n is some x which is not equal to 1, then it implies that either x divides both A comma n, or x divides both B comma n. But if x divides both A comma n, that means the GCD of A and n is not 1, but rather x, and x is not equal to 1, but that is a contradiction, because GCD of A and n is 1. In the same way, x cannot divide both B and n, because if that would have been the case, then GCD of B and n would have been x, but not 1, but that is again a contradiction to this fact. So, that is why, since both A and B are co-prime to n, I can say that their product is also co-prime to n. Okay. And by the divisibility property, I get that R is equal to the difference, R will be the difference of A times B and some multiple of n. So, now combining these two facts, I can conclude that the GCD of R and n is also 1. Okay. That is very simple, right. So, that shows that R is a member of Z n star as well, and R is the result of A multiplication B modulo n. So, the closure property is satisfied. Now, let us see associativity property is satisfied or not. So, if you take any triplet of elements A, B, C, all of which are individually co-prime to n, and multiply them together and you perform the multiplication modulo n operation involving two elements at a time, then it does not matter in what order you perform the multiplication modulo n operation, the result will be the same as if you multiply A, B, C and then you take modulo n. So, of course, the result will be an element in the range 0 to n minus 1, and at the same time it will be co-prime to n, right. Namely, if R is the remainder obtained by dividing A, B, C by n, then R has to be co-prime to n, because if R is not co-prime to n, then you get a contradiction that either A is not co-prime to n, or B is not co-prime to n, or C is not co-prime to n, which is not true. the element 1 will be a member of Z n star, because GCD of 1 comma n is indeed 1. This implies the element 1 belongs to Z n star. And now you perform the multiplication modulo n involving any element A from Z n star and the element 1, the result will be the element A itself. And now what about the inverse? So, if you are given an element A from Z n star, that means the GCD of A and n is 1, then there is one wonderful result from number theory, which says that if A is relatively prime or co-prime to your modulus n, then there always exists another integer B also from your set Z n star, such that the result of A multiplication B modulo n will give you the identity element, namely 1. So, the element B will be considered as the multiplicative inverse, multiplicative inverse modulo n. And it is easy to see that if B is the multiplicative inverse of A modulo n, then A will be considered as the multiplicative inverse of B modulo n. That means, they are inverse of each other. Okay. So, that means A inverse will be B and B inverse will be A, because of the fact that when you multiply A and B and take modulo n, you get back the identity element 1. So, now let us see some concrete examples of the two special groups Z n and Z n star that we have encountered. So, here let us see first n equal to 6, and with respect to the addition modulo 6 operation. So, I have drawn a table here. Along the rows you have the elements of along the columns you have the elements of Z 6, and along the rows you have the elements of Z 6. So, you can imagine that along the columns you have the candidate values of A, along the rows you have the candidate values of B, and then the various entries will denote the result of performing A plus B modulo 6. So, for instance, if I take 0 and 0, add them and take modulo 6, the result will be 0. If I take 0 and 1 and then add them and take modulo 6, I will obtain 1, and so on, right. In the same way, now if I take if I take the element 1 and add it with 0, I will obtain 1, and 1 modulo 6 will be 1, and so on. So, this entry let us verify. So, if I add 1 to 5, and then if my operation is modulo 6, this will be 6 modulo 6, and 6 modulo 6 is 0. So, that is why we get the result 0 here. In the same way, the third row will be this, fourth row will be this, fifth row will be this, sixth row will be this. So, now you can see that it does not matter what is the value of A, what is the value of B, the result is always an element of the set Z 6. Remember, my set Z 6 will have the elements 0 to 5. Okay. Nowhere we obtain an element which is outside the set 0 to 5. Okay. The associativity property is always satisfied. The element 0 is the identity element, because you add 0 with 0, you get 0. Okay. You add element 0 and 1, you obtain the element 1. You add 0 and 2, you obtain 2, you add 0 and 3, you obtain 3, you add 0 and 4, you obtain 4, you add 0 and 5, you obtain 5. So, that means if you want to find out the identity, just focus on the row involving 0, and if you want to find out the inverse of various elements, okay, then you can verify here that the inverse of 0 is sorry, the inverse of 0 is 0, the inverse of element 1 is element 5, because 5 plus 1 will be 6. So, basically 1 inverse will be considered as minus 1, and as per our definition of minus 1 it will be 6 minus 1, which is 5. And indeed if you add 5 to 1 and take modulo 6, you will obtain the identity element namely 0. In the same way, the inverse of element 2 will be element 4, because 2 inverse is basically minus 2 in the set Z n, and minus 2 is nothing but 6 minus 2, and 6 minus 2 is 4, and so on. Okay. Now, let us take the example of Z n star, and I take here n equal to 7. So, your Z 7 will have the elements 0 up to 6. Okay. Now, Z 7 star will have all those elements from Z 7 which are co-prime to 7. So, it turns out that 0 is not co-prime to 7, because if I take GCD of 0 and 7, then it turns out to be 7. That is the highest that is the largest number which divides both 0 as well as 7, and that is not 1. So, that is why 0 will not be included in Z 7 star, but if you take the remaining elements, all of them are going to be co-prime to your modulus 7, because 7 is the prime number, and that is why Z 7 star will have the elements 1, 2, 3, 4, 5, 6. So, again I have done the same thing along the row along the columns. I have denoted the candidate values of A, along the rows I have denoted the candidate values of B. Well, you can interpret it other way around. You can imagine that along the rows you have the A's and candidate A's, and the columns you have the candidate B's. And now, let us see the result of performing A multiplication B modulo n. So, 1 multiplied with any number, and then if you perform modulo 7 you will obtain back the same number. So, the row under A is not interesting. Let us consider the row under 2. So, if you perform 2 multiplication 1 modulo 7, that will be same as 2 modulo 7, and hence 2. If you multiply 2 with 2 and take modulo 7, that will be 4 modulo 7, which is 4. But now, if you perform multiplication of 2 and 3 modulo 7, that will be 6 modulo 7, that will be 6. But as soon as you perform 2 multiplication 4 modulo 7, that will be 8 modulo 7, and 8 modulo 7 is 1. So, you can see now. And similarly 2 modulo 2 multiplied with 5 will be 10, 10 modulo 7 will be 3, and so on. The same way you can find out the remaining rows. You can see the closure property is satisfied, because you always obtain a result which lies within the set 1 to 6. The element 1 will be the integer 1 will be the identity element, and the inverse of 1 will be 1, inverse of 2 will be 4, because when you multiply 4 with 2 and then take modulo 7, you get the identity element 1. So, the inverse of 2 is 4, and now let us check the inverse of 4. Okay. The inverse of 4 will be 2, because this particular entry is the identity element. So, under the column 4, under the row 2 you obtain the element 1, that is why the inverse of 4 is 2. So, that is why what I said earlier is correct, you can verify that. If A is the inverse of B, multiplicative inverse of B, then if B is the multiplicative inverse of A, then A will be the multiplicative inverse of B, and so on. So, what will be the cardinality of the group ZP star if P is a prime number? So, as we have demonstrated here, ZP star will have all the elements from ZP except the element 0, because the GCD of 0 and P will not be equal to 1, because it is P. Other than that, all other elements in the set ZP will be co-prime to your P. Okay. So, with that I end today's lecture. These are the references used for discussing today's concepts. Of course, they are very basic facts about groups, you can find them in any online resource. Thank you.